we do that? Well, actually, there are only two files that have to be modified, and they are, if we take a look at the repository, no, no funciona eso. No funciona el mouse. No responde. Anyway, okay, if we take a look at the repository, we'll see that we have to tell Kratos that we have our application. As Carlos was explaining before, if we go to the CMake build folder, here we have the configure.sh. So if we take a look here, the only thing we would have to do is add the new application. As you can see here, it's a list of all the applications that are going to be compiled or not compiled. So we just have a new flag like this for the Pure Diffusion application. And once we have done this, we do the same thing, but for the in the applications folder, there's a file that contains how the exact location of the folders. Oh, sorry. Yeah. Okay, so you see here, we in this case, if the flags are on, the ones we are interested in, we just define where it's the folder that we want. So actually, by just modifying these two little files, our Kratos will be able to see our application. So we just execute the script. It's automatically renamed to the name that we want, and then we modify these two files, and automatically it will be compiled. The next time we compile Kratos, Kratos will know that we have added an application, and will actually, if you execute it, you will be able to see it. But so far, our application is empty. So it's so if we take a look at the Pure Diffusion application that we created, it's basically empty. There's only declarations of variables and elements. So actually, if we execute Kratos and then we import our application, you can see here that we are only declaring registering the new variables, but there's nothing left. It's not real tasks, let's say. We're just telling Kratos, okay, you have called me, and these are the elements that I have and the new variables that I have. So actually, it's not much that can be done. So actually, it's not a big deal in programming, because what we actually want to do is we want to add the elements, and all the rest will be done by the Kratos core. Okay, so how do we create an element? Well, when we want to create an element, we have to create a right-hand side and a left-hand side matrix. Ricardo will be talking about this in a minute. But basically what we have to do is we create the matrix, and then we tell Kratos in which position, according to the global system, it's assembled. It's the same for the conditions, and then also if we wanted to create a utility, it will also be possible. In which cases are utilities useful? For example, let's suppose you have a task that cannot be done by the element. For example, you need information from the whole domain. So actually just focusing on a single element, it's not enough, because you want to gather information from each element and then do a global computation. So in this case, when you cannot find anything on the core that it suits your need, you can create your utility. In this case, if you want to create one, it's also quite simple. By just modifying two files, you're going to tell Kratos that you have an utility. So, for example, in this case, we're going to calculate the mean temperature of the domain. So this could be our utility. As you can see, it's quite simple. It's programmed in C++. And then we would have a loop on the elements. We calculate the mean temperature on each element. We add the temperature of all the elements, and then we divide by the total area. So that will be it. It's quite simple. This is a whole file. So as I was telling you before, the only thing we really have to program was the elements and the conditions, because all the other things can be done by the Kratos core. Okay, so we have to tell Kratos what we wanted to do. Since we're not going to do it in C++, we're going to do it in the Python files, as Puyan was showing you before. So how are we going to do this? Well, we're going to create our elements with the initial data, and then this will be the Python scripts. Basically, as you can see here, this is the example of our files. We import the applications as Puyan told you before, and then we'll add the variables. And as you can see here, we are going to import another Python file that is contained within the folder of the application that we created. So as you can see here, when we import this file, we have access to all this information. So we'll add the variables here, that is contained here, and also we add the degrees of freedom, and finally we're going to solve the systems. It's interesting to notice that, well, this is in case we want to call the utility. It's important to notice that if you wanted to use another solver that is in another application, it's also quite straightforward. For example, adding several applications is just done by importing the other application. And then they are going to see, it's possible to see the other application also. For example, if you want to solve the system with a different solver, the only thing we have to do is we import the external solvers application that has iterative solvers. We also do it in the pure diffusion solver, the same thing. And finally, when we want to declare the solver, instead of using the standard solver that we were using before, we're going to use the new solver that was provided by the external solvers application. So as you can see here, combining several applications is quite straightforward. Not only for a solver, but also if you wanted to use, for example, a meshing application, remeshing the domain, using particles or anything that you wanted, by doing this by the Python files, it's actually quite easy, because when you compile the applications, it's not needed that they see each other, but you just can do it everything in the Python. So actually that's the main advantage of working with Python, that you have complete flexibility without the need of of recompiling the whole code. Okay, so that's it, and thank you for your attention. Any questions? Yeah.
Can I know what was the problem which you solved, which was related to temperature?
No, actually, it was just basically the equation we are solving is the Laplacian system. We just have the diffusion equation, and that's it. It was, well, actually, if you take a look at the tutorial, everything is explained there. I was just trying to be brief.
There was no physical problem which you solved in that?
So what do you mean physical?
I mean, any case study of anybody having different temperatures, that's like that.
Sorry?
No, there was no case study, I mean?
Well, actually, this is just a heat conduction problem.
Your results were showing the variation of temperature, that's what I was saying.
Yeah, this is I added a load in this node, and then I fixed the temperature on this node, and this is everything that is done. So no, it's just the most simple problem you could think of. The idea is to show that actually by just modifying two files and downloading the application from the internet, you can create your own application and you have complete freedom. If you want to stray strictly on finite elements and just assemble the system and solve it, then it's quite easy. If you want to get deeper and be more flexible, it's also possible. But if you just want to do standard things, it's really, really easy to do. But of course, if you want to get more crazy things, you can always create your utility, and there you can have complete control on what you do. That's the idea. Okay.
For linking GID with any extended Kratos that you have done?
Well, actually, there's I don't know. Did you show the? Actually, there's an interface on Git to export the files that are read by Kratos. So actually, you can just when you go to GID, you can go to import problem type, and you can already get it from the internet. So actually, you can get the pre-processed files for Kratos directly from GID. So it's really, really easy to do. And also the post-process format that is used in Kratos is already ready for Git.
No, yeah, but imagine you do your own strategy or your own application, and you want to call it from GID.
Well, yeah.
Problem type generator also.
Custom
Custom problem type.
ad hoc for your application. So I have the honor to be the last one to speak today. And I don't have the time here, but I know that we are behind schedule. So I'll try to be quick. What I want to do today, so now, is just to explain very briefly how to create a new element. And I will also say an element and a condition, because the two things are related one to the other. Really, more than explaining the steps, I would like to just point out the things you need to understand when you create a new element. So I will say what you need to do, but mostly what you need to understand when you're going to put a new element. And first of all, the thing we need to understand is what an element is. Okay? So an element is a finite element, but essentially it's the place in which you're going to put the physics you want to put in the system. So that's how the system, which is essentially a big database and a collection of utilities or of solvers or whatever, the element gives to this big system the physics you want to solve. So you will have an element for convection diffusion and a different element for structural mechanics, right? So what is the idea? The idea is, Pablo already put a bit of this before, but an element needs to do a few essential things, okay? So it needs to tell to the Kratos, to this big collection of utilities, how to create a duplicate of itself, and that's the function create. It has to give the local contributions, so essentially you need to say what is the right-hand side and what is the left-hand side that will be built up in a big matrix and will describe the problem. This is the function calculate local system. Then you may want to compute at the same time a left-hand side and the right-hand side, and then you will need to provide a calculate right-hand side. This does not say what the matrix is. It just says what the right-hand side of the big system is. So these are minimal functions, but then it also needs to say, okay, I have this small contribution that's local, and I need this contribution to be in that exact place of the system, okay? In the first two rows and not in the last two, okay? The way to do this is through the equation ID vector. So the element has to say, I want to be assembled in that specific position of the big matrix, okay? So that's another function we need to provide. And finally, we need to inform the system not just of where it is, but of what kind of variables the element will be operating on. And then I will have to define get_dof_list. So essentially, the element needs to say the DOFs I'm interested in being solved for are the ones provided by this. So this collection of 1, 2, 3, 4, 5 function is essentially what the minimum that you can give to provide to the Kratos a description of the problem, of the physics you want to solve, you want to implement in your element. Now, really, before going in saying, okay, this is the function you need to do, you need to modify this line and you need to do a new element. And more than describing that, I will give you, okay, this is where you can read it. We need to understand what is the right-hand side and the left-hand side. So what are these two things, this vector and this matrix, that need to be assembled, okay? I'm stressing this because we are maybe not completely standard in the way we do this. What is important is that we targeted our design to the solution of nonlinear problems, okay? And for a nonlinear problems, then it is customary to assume that the right-hand side it is a residual. What does it mean? It means that if you want to solve a linear system, you normally write A times X equal to B. So your stiffness matrix times the solution you want to obtain is equal to the external forces or sources or whatever you want. That's not what we do. What we do is that our right-hand side are the external forces minus the internal forces. That's always the unbalance of the solution we want to solve for, okay? This means that if X is the unknown, what we want to solve for, we are going to have this right-hand side defined in principle as a function to be minimized. Our objective is to have the right-hand side to be 0 when the X is found. And we will define the left-hand side as the derivative of such right-hand side with respect to the x. If you understand this, I'm sure it will be very easy to write an element, okay? In the practice, the thing is very easy if you have a linear element. For example, if you have a temperature element, then what will happen is that the external forces will be constant. That's a vector that is constant. Imagine the sources in your linear diffusion problem. The forces, if you have a structural problem, that's a constant vector. And the internal forces for a linear problem are really the stiffness matrix times the solution you want to get. Now, if you look this, we will have that our residual is the external forces minus the internal forces. And then what we'll have that our residual will be the external forces minus the product between the elemental stiffness matrix and the solution we want to get. Okay? That's why many of the elements are made this way. But also, if we now take the derivative of this, then the derivative of this thing here, well, actually it should be a minus here, really. But the derivative of this is directly k. So for a linear element, the left-hand side is the standard one. But what is non-standard is the right-hand side that is written in the form of a residual. Now, really, that's what you need to know to understand. And that's how you can add the new element. And now, if you want to have an element, to add an element, and you want to solve for it, then you have to let the Kratos know that this element exists. Okay? So what you need is to take your element, your CPP that you implemented, and you need to add to the list of files that need to be compiled. Then what you need to say is, okay, now I need to create a prototype object, and I need to take this prototype object and to put it in the file that defines the application. There are two. There is typically application name.h and application name.cpp. I will show you where. What you need to do is to have an object in the H defined there, allocated in the CPP, and then every time you will need to have a new element, we will take this prototype and we will create a copy of it with new data. Okay? What we need is that we need to give a way to identify with a string this element. Okay? So we need to say that if we call convection element, then this element will be mapped. When we write convection element, we'll need to know that our prototype is convection element, is the one that we defined. And then we need to define this function that does automatically what you need to do. So there is a call to register element. I'm going to show you an example very briefly, but essentially you need to say that this name, that will be the name in which you will recognize it from the Python or from the MDPA, is associated to this prototype element. Well, that's all. Now, another thing you need to do, maybe it's not as important, but you need to understand that elements are designed to be run in parallel. Okay? So if you want your element to work correctly with the rest of the Kratos, you need to ensure that two elements can be handled at the same time by two different processes. It means that they are thread safe, but there is just one thing that you need to understand, and it is that new elements should only modify the elements that you are passing to them, the parameters you are passing to them. An element has a pointer to a node. So in principle, an element could take a value of a node and could change that. Okay? You can do it, but if you do it, it's at your own risk. You shouldn't do that, because if you do, your element is not thread safe, and then you cannot ensure that this element will work correctly in parallel. Okay? That's what I'm telling here. Now, if you need to obtain data from the element, there are two functions, two interfaces for that. One interface is calculate, to get one single value from an element. It can be whatever. It can be, the output is controlled by a variable. And this is also a function, calculate an integration point, that gives you back the result you want, controlled by a variable again, but not one single result for the element, rather one result per every of the Gauss point of the elements. Okay? The use of geometry. The use of geometry is something we need to understand also. We need to understand that an element defines the formulation you want to implement, okay? But the topology, the shape of the domain, is defined by the object geometry. So when you define an element, you're telling it, I'm defining your element, and you are going to work with a tetrahedra, say, or with a quadrilateral. So there is an object, it is this geometry, that gives you the way to handle this. For example, if you are passing 4 nodes, for example, it could be a quadrilateral in 2D, or it could be a tetrahedra in 3D, okay? The geometry will know that the shape function should be computed differently in 2 dimensions or in 3 dimensions. And your element could abstract from that. So it is possible to write an element that works both in 2D and in 3D, for example, and that always asks to the geometry all what it needs for. There is an example. If you click this, we'll publish this PDF. If you click here, there is a link to how to use the geometry that is in the wiki that gives you examples on how you can iterate, how you can obtain shape functions, all of that to write your element. Then also an element has properties. And having properties, it means that there are pointers to things that are in common between a big group of elements, and then you can put things that are common to many objects. For example, the density. You could have that the density is common to all the elements in a big structure, or not, of course, okay? But if you assume this, then the place to put that is this entity which the element has, that is the property. The last thing I need to say is that if you need to pass any parameter to the element, then the standard way is through this container, which we pass to every function, that is the process info. The process info is a container that contains the data of your solution up to this point, for example, the time at which you are, the delta time, but could also contain new variables, and that's the way in which you can pass unexpected values, let's say, to any element or to any function within the element. For example, if you need to have an element that does multiple stages, you could say, I am at stage 1, you would define a function, a variable stage, and you could pass this function through the process info so that the element can see at which stage it is, and it could behave different for the first stage of a computation or for the second stage of a computation. And then there is a last thing. I think this is the last slide, I hope. But elements provide a function check. Now, it is not vital. You can live without writing a function check. But that's useful if you do, because there are things that are common. For example, you wrote an element in 2D, and you expect this element to be in the XY plane, okay? And someone defines you the element in the YZ plane. May happen, okay? And the element will not work, I can assure you that, because it happened to me, okay? Many times, actually. Well, if you want to have one place in which you check if you are in the correct place, one place that is correct just once in all your calculation, then it's the function check, okay? At a certain point at the beginning of your calculation, you go through all of your elements, and you say check. And these checks, I don't know, if you have a constitutive law, because if you don't have a constitutive law and you want to solve a structural problem, probably you're going to fail, okay? That's the sort of thing you can do in there. Okay, it was not the last, two more. There are elements and there are conditions. What are elements and conditions? Are conceptually very similar, but the elements implement the behavior of the volume, and the conditions implement boundary condition, let's say. For example, the application of forces, Neumann condition, things that need the evaluation of integrals over the boundaries. Okay? Well, one more. That's it. Okay, that was the last. So with this, I think I'm done, and I hope it was not too long. Well, that's over. I hope I gained some time.